Hello, in this lecture we will answer on two questions. The first question is to find out the area of this semicircle that is inscribed by a quarter circle, and in the second question we will find out the size of this angle, angle theta, that is the angle of this right triangle, triangle ABC. So we'll start with the first question. In this question, we have in the drawing a quarter circle, and we have this semicircle that is inscribed by this quarter circle. So here, first of all, we will define the center of this quarter circle. Here we define the center of this quarter circle at this point, point O. And then I will present to you a new rule, that is rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So I read rule number 1 again. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we also have tangent AB, here this tangent AB is tangent to this circle at this point. Point M is the point of tendency of tangent AB with this circle. So point M is the point of tendency of tangent AB with this circle. and point O is the center of this circle, and we have the radius OM. OM is the radius of this circle, so we will define it as R. So here the radius OM is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle, and whenever we have a radius that is drawn to the point of tendency, like in this drawing, then the tangent will be perpendicular to that radius. In this case, tangent AB will be perpendicular to the radius MO. That is to say, AB is perpendicular to MO. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So whenever we have a radius that is drawn to the point of tendency, like in this case, then the tangent will be perpendicular to that radius. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay, so we can implement rule number 1 in our drawing. Here we define this point as point A. This point will be point B. This point will be point C. This point will be defined as point D. This point will be defined as point H. This point will be defined as point F. And this point will be defined as point G. Here we join points on B together by a straight line. OB is the radius of this semicircle because of the fact that it starts from the center of this semicircle, that is to say from point O, and ends at point B, that is a point on the semicircle itself. So OB is the radius of this semicircle, therefore we define it as R. So we have the radius OB of this semicircle that is drawn to the point of tendency. That is to say, the radius OB is drawn to point B, that is the point of tendency of tangent AC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent AC will be perpendicular to the radius BO. So AC is perpendicular to BO. AC is perpendicular to BO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we will join points O and D together by a straight line. Here, line segment OD is also the radius of this semicircle because of the fact that it starts from the center of the semicircle and ends at point D, that is a point on the semicircle itself. And this is exactly the definition of a radius. So OD equals to R, that is the radius of the semicircle. And here we have the radius OD that is drawn to the point of tendency. That is to say, it is drawn to point D, that is the point of tangency of tangent CH with this semicircle, and whenever you have a radius that is drawn to the point of tangency, then the tangent will be perpendicular to that radius. In this case, tangent CH will be perpendicular to the radius DO. So CH is perpendicular to DO, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. And here, because of the fact that ACH is a quarter circle, then C must be the center of the quarter circle. I write it down. Point C is the center of the quarter circle. So point C is the center of the quarter circle, and angle ACH is a right angle. So angle ACH is equal to 90 degrees. It is a right angle. So actually, in quadrilateral BOCD, we have 3 right angles. 1, 2, 3. I'll repeat again. In quadrilateral OBCH, we have 3 right angles. 1, 2, 3. So I write it down. In quadrilateral BOCD, we have 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees. Plus the size of the fourth angle, that is actually angle BOD. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we will subtract 270 degrees from this equation, and we will get that the missing angle BOD is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees. So we found out that the missing angle BOD is a right angle, it is equal to 90 degrees. So this angle is a right angle. So therefore, in quadrilateral BOCD, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral BOCD as a rectangle. I write it down. Quadrilateral BOCD is a rectangle because it has 4 right angles. Quadrilateral BOCD is a rectangle. And we have also rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of rectangle BOCD are equal to each other. It means that BO is equals to CD. Again, BO, side BO equals to side CD according to rule number 2. I repeat again, according to rule number 2, side BO equals to side CD. The opposite sides of rectangle are equal to each other, therefore BO equals to CD in rectangle BOCD, but BO equals to R, it is the radius of the semicircle. So we can write here that BO equals to R, and from this equation R equals to BO equals to CD, we will derive that CD is also equals to R. CD is also equals to R. So we can write here that CD equals to R. Likewise, according to rule number 2, OD must be equal to BC. OD, side OD of rectangle BOCD must be equal to side BC according to rule number 2, that the opposite sides of rectangle are equal to each other. Again, side OD must be equal to side BC, but OD equals to R, it is the radius of the semicircle. Here OD equals to R, and from this equation R equals to OD equals to BC, we will derive that BC is also equals to R. BC is also equals to R. Here BC equals to R. So actually we found out that all the sides of rectangle BOCD are equal to each other. All of its sides are equal to R, and it has 4 right angles. Therefore, quadrilateral BOCD is not a rectangle but a square. So we can find out that quadrilateral BOCD is a square. Okay, I'll repeat again. Quadrilateral BOCD is a square because all of its sides are equal to each other and all of its angles they are equal to 90 degrees. So in the next step, we'll join points C and O together by a straight line. And in order to find out the length of diagonal CO of square BOCD, we will implement the Pythagoras theorem on the right green triangle OCD. Okay, so in the right green triangle OCD, according to the Pythagoras theorem, here PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OC square equals to CD square plus OD square. repeat again. According to the Pythagoras theorem, on the right great triangle OCD, OC square equals to CD square plus OD square, so OC square, which is the square of the hypotenuse, will be equal to CD square. Here, CD equals to R, so CD square it is equal to R square plus OD square. OD equals to R, so OD square will be equal to R square. So in conclusion, we found out that OC square equals to R square plus R square. R square plus R square equals to 2R square. Here we take a root out of this equation and we get that OC, the diagonal OC of the square, it is equals to square root of 2 times R. Okay? Here, the diagonal OC equals to square root of 2 times R. In the next step, we will extend diagonal CO by a straight line until it touches the quarter circle, and this point S. Point S is the touching point of the extended CO and the quarter circle, and we will find out the length of the small line segment SO. So here it is easy to see that line segment SO equals in its length to SC minus OC. I repeat again, the small line segment SO equals in its length to SC minus OC. Again, SC minus OC equals to the length of line segment SO. So the length of line segment SO will be equal to SC. Here, what is the length of line segment SC? C is the center of the quarter circle. I repeat again, C is the center of the quarter circle, and S is the point on the quarter circle itself. And this is exactly the definition of a radius. So CS is the radius of the quarter circle, and it is given as the question that the radius of the quarter circle equals to 3 units. So SC equals to 3 units. It is the radius of the quarter circle. It is given as the question. And OC, we just right now found out that OC, the diagonal of the square BOCD, equals to square root of 2 minus square root of 2 times R. So in conclusion, we found out that the length of line segment, the small line segment SO equals to 3 minus square root of 2R. Here SO equals to 3 minus square root of 2R. Okay? Again, SO equals to 3 minus square root of 2R. In the next step, I will complete the quarter circle to a circle. Okay. Here. So we completed the quarter circle to a circle, this circle, and in the next step we will extend the diagonal OC by straight line until it touches the circle and we will define the touching point of the extended diagonal OC with this circle as point M. Again, point M is the touching point of the extended diagonal OC with this circle. So what is the length? What is the length of line segment CM? The length of line segment CM, it is the radius of the quarter circle. Why? Because point C is the center of the quarter circle and point M is the point on the circle itself. And this is exactly the definition of a radius. Any line segment that starts from the center of the circle or quarter circle and ends at point M, that is a point on the circle itself, then it will be the radius of this circle. That is to say, we know that the radius of this circle is equal to 3 units because it is the same radius, the radius of the quarter circle and the radius of the circle itself, it is the same radius. Therefore, it is equal to 3 units. Okay, so MC, the radius of the circle, it is equal to the radius of the quarter circle, that is 3 units. In the next step, I will present to you a new rule. That will be rule number 3. According to rule number 3, if chord AB intersects with chord CD at point O, point O is the intersection point of chord AB with chord CD, then AO times OB is equal to CO times OD. So according to rule number 3, if we have chord AB, this chord AB intersects with chord CD. This is chord CD. I repeat again, chord AB, the red chord, intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. Then, according to rule number 3, this rule, AO times OB equals to CO times OD. Again, whenever you have two chords that intersect with each other, like in this drawing, chord AB intersects with chord CD inside the circle, then AO times OB equals to CO times OD. So we actually can implement rule number 3 in our drawing, because in our drawing we have chord SM intersects with chord GF, this chord, chord SM intersects with chord GF at point O. So point O is the intersection point of chord SM with chord GF. Therefore, but before that, what is the length of line segment GO? O is the center of the semicircle. D is a point on the semicircle itself. Therefore, GO is the radius of the semicircle, that is to say it is equal to R. Likewise, for the same reason, OF, it is also the radius of the semicircle, that is to say it is equal to R. Why? Because O is the center of the semicircle. F is a point on the semicircle itself. Therefore, OF is the radius of this semicircle, that is to say it is equal to R. So according to rule number 3, we get that MO times OS, MO times OS equals to GO times OF, equals to GO times OF. I repeat again, in our drawing, according to rule number 3, MO times OS equals to GO times OF. And what is the length of line segment MO? It is very easy to see from the drawing that the length of line segment MO equals to MC plus CO. MO equals to MC plus CO. Again, MO equals to MC plus CO. Okay, MO equals to MC plus CO. And we have already found out that SO equals to 3 minus square root of 2R. SO or OS, it is the same. It is equal to 3 minus square root of 2R. And it is equal to GO, that is R, times OF, that is also R. So in conclusion, we found out that MC plus CO times 3 minus square root of 2R equals to R times R. So R times R is R squared, and R squared equals to MC, MC equals to 3, and CO equals to square root of 2R. So in conclusion, MC plus CO equals to 3 plus square root of 2R times 3 minus root of 2R equals to R squared. So this expression 3 plus 2R times 3 minus 2R, it is very similar to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. Okay, and in our specific expression, A is equals to 3 and B equals to square root of 2R. So A squared will be equal to 3 squared, that is 9, minus B squared. So this expression equals to A squared minus B squared. A squared equals to 3 squared, that is 9, minus B squared. B equals to square root of 2R, so B squared will be equal to square root of 2R squared. Square root of 2 is 2 times R squared. So in conclusion, we found out that this expression equals to 9 minus 2R squared, and it is equal to R squared. So here we will add 2R squared to this equation, and we'll get that according to this equation 9 equals to R squared plus 2R squared is 3R squared. Here we'll divide this equation by 3 and we'll get that 3R squared over 3 is R squared. R squared equals to 9 over 3, that is 3. 9 over 3 is 3, so in conclusion we found out that R squared equals to 3. And what is the area of this semicircle? The area of this semicircle equals to the area of the circle over 2. And the area of the circle is pi r2. Therefore, the area of the semicircle will be half of it. That is to say, the area of the semicircle will be equal to pi r squared over 2. Okay? I'll write it down that the area of our semicircle will be equal to pi r squared, but we have already found out that r squared equals to 3, so we'll substitute r squared in this equation by 3 and we'll get that the area of our semicircle equals to pi and r squared is 3 over 2. That is to say, in conclusion, the area of the semicircle equals to 3 pi over 2 square units, or in terms of numbers, it is equals to 3.71 square units. Okay, so I'll repeat again. The area of our semicircle, the area of this semicircle that is inscribed by a quarter circle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first method. In the next step, I will present to you how to find out the area of the semicircle according to the second method. In the second method, we'll use the things that we have already found out in the first method. Here, point O is the center of the semicircle, and this is point A, and we've already found out that quadrilateral OBCD is a square, C is the center of the quarter circle, and this quadrilateral BOCD is a square, and we have already found out that OC, the diagonal of this square, it is equal to square root of 2r. This is point G, this is point F, and we have already found out that GO is the radius of the semicircle, that is to say it equals to r, and OF, it is also the radius of the semicircle, that is equal to r. In the next step, we join point C and F together by a straight line. So what is the length of line segment CF? According to our definition, we've already found out that C is the center. We know that C is the center of the quarter circle, and F is a point on the quarter circle itself. Therefore, this is exactly the definition of a radius. That is to say, CF is the radius of the quarter circle, and we know that the radius of the quarter circle equals to 3 units. So here CF equals to 3 units, and we will also join point C and G together by a straight line. So here CG or GC, it is also the radius of the quarter circle for the same reason. It is equal to 3 units. Why? Because C is the center of the quarter circle, and G is a point on the quarter circle itself, and this is exactly the definition of a radius. Any line segment that starts from the center of the quarter circle and ends at any point on the quarter circle itself is defined as a radius. Therefore, CG is also the radius of the quarter circle. That is to say, it is also equals to 3 units. So here, triangle GCF is an isosceles triangle. I will write it down. Triangle GCF is an isosceles triangle. Because of the fact that side CG is equal to side CF in triangle CGF. And GF GF is the base of the isosceles triangle, triangle CGF. Okay, GF is the base, of the isosceles triangle, triangle CGF. And CO is the median to the base GF. Why CO is the median? Because of the fact that line segment CO divides the base GF into two equal parts. For that reason, CO is the median to the base GF. CO divides the base GF into two equal parts. Why? Because GO equals to OF equals to R. So we copy the right triangle, triangle GCF in a new page, and we will analyze the right triangle, we will analyze the isosceles triangle, triangle GCF. Okay? So this is the isosceles triangle, triangle CFG. FG is the base of the isosceles triangle, triangle CFG. Here, triangle CFG is an isosceles triangle. Here the base of the isosceles triangle, triangle CFG is FG, and the median is CO. Why the median is CO? Because the median because line segment CO bisects the base FG into two equal parts. FO equals to OG equals to R. Okay? And we actually have rule number 4. It relates to the median to the base of an isosceles triangle. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. I'll repeat again on rule number 4. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So here, according to rule number 4, the median CO to the base FG of the isosceles triangle CFG is perpendicular to the base FG. So here, CO is perpendicular to the base FG. Again, CO is perpendicular to FG. That is to say, according to rule number 4, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? I will repeat again. According to rule number 4, the median to the base, that is to say, the median CO to the base CG, is perpendicular to the base. So the median CO perpendicular to FG. So if CO is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So we actually the median CO created two right triangles. It divides the isosceles triangle CFG into two right triangles. So if we focus on the right triangle COF, we have already found out that the length of the median CO, it is actually equals to square root of 2 times R. So I'll copy the right triangle COF in a new page, and we will implement the Pythagoras theorem on this right triangle COF. Okay? So in the right triangle COF, again, this angle equals to 90 degrees according to rule number 4. The median CO equals to square root of 2 times R. We already found out in the first method that CO equals to square root of 2 times R. And FO is the radius of the semicircle, that is to say it is equal to R. And CF is the radius of the quarter circle, that is to say it is equal to 3 units. So here, according to rule number 4, the median CO to the base GF, here the median CO to the base CF is perpendicular to the base GF. Again, the median CO to the base GF is perpendicular to the base GF. So CO is perpendicular to GF, that is to say, if CO is perpendicular to GF, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So we will focus on the right triangle CFO. So I copied the right triangle CFO in this new page. We implemented the Pythagoras theorem in the right green triangle CFO. According to the Pythagoras theorem, in this right triangle CFO, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, CF square equals to CO square plus FO square. CF equals to 3 units, so CF square is 3 squared, that is 9, and it is equal to CO square. CO equals to square root of 2r, so CO square will be equal to 2r square plus FO square. FO equals to r, so FO square will be equal to r square. So in conclusion, we found out that 9 equals to 2r square plus r square, this is 3r square. Here we will divide this equation by 3, and we get that 3r square over 3 is r square, and 9 over 3 is 3. So in conclusion, we found out that r square equals to 3 units. And we know that the area of the semicircle equals to pi r square over 2. R square is 3. So here we'll substitute r square by 3. So it will be equal to pi, and r square is 3 over 2. So in conclusion, we found out that the area of the semicircle equals to 3 pi over 2 square units. So in terms of numbers, it is equal to 3.71 square units. Okay. I'll repeat again, the area of the semicircle, according to the second method, it is equal to 3 pi over 2 square units. So in terms of numbers, it is equal to 4.71 square units. Okay, so we finished with the second method. In the next step, I will present to you the second question. In the drawing, we have the right triangle ABC. We know that side BC of the right triangle ABC equals to 6 units. And we also know that line segment AE equals to EC. We know that angle ABC, this angle equals to 90 degrees. And we also know that line segment DE equals to 2 units. And we also know that line segment DE is perpendicular to the hypotenuse AC. And we want to find out the size of this angle theta, that is actually angle BAC. Okay? I repeat again that we want to find out the size of this angle BAC, that is equal to theta. So we'll start with the first method. In the first method, we will do a construction from point E. We will draw perpendicular on BC. Again, from point E, we will draw perpendicular on BC. So this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. And we will define the touching point of the perpendicular from point E and BC as F. In the next step, we will define angle ACB as alpha. And in the right triangle, triangle ABC, angle ABC equals to 90 degrees. Angle BAC equals to theta. So angle ACB, this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC to 180 degrees. Why? Because 90 degrees minus theta plus theta equals to 90 degrees. And 90 degrees minus 90 degrees plus 90 degrees equals to theta. So that is the reason that this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC to 180 degrees. So, in conclusion, we actually found out that alpha equals to 90 degrees minus theta, because alpha, angle ACB equals to alpha according to our definition from one side, but from the other side, we just now found out that this angle must be also equals to 90 degrees minus theta. Therefore, alpha equals to 90 degrees minus theta. Okay? So alpha equals to 90 degrees minus theta. So we will add theta to this equation and we will subtract alpha, and we will get that theta equals to 90 degrees minus alpha. So in the right triangle, the right small triangle, EFC, in this right triangle, angle EFC equals to 90 degrees, angle ECF equals to alpha, so this angle FEC must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right triangle FEC to 180 degrees. This angle must be equal to 90 degrees minus alpha. And what is the size of angle DEF? The size of this angle DEF, it must be equal to DEC minus FEC. Again, DEC, angle DEC, this angle minus angle FEC will be equal to angle DEF. I will write it down. That the big angle DEC, minus angle FEC it will be equal to the missing angle DEF, this angle. I'll repeat again, angle DEF equals to angle DEC minus angle FEC. So this angle angle DEF equals to angle DEC, that is 90 degrees according to what is given as the question. Minus angle FEC, and according to what we have already found out, angle FEC equals to 90 degrees minus alpha. So we substitute angle FEC by 90 degrees minus alpha. So in conclusion, we found out that the missing angle DEF equals to 90 degrees. We will open the brackets here, so it is 90 degrees minus 90 degrees, that is 0. Minus and minus is plus alpha. So in conclusion, we found out that the missing angle DEF equals to alpha. Okay, angle DEF equals to alpha. So actually, in the right triangle DEF, this angle equals to 90 degrees. This angle equals to alpha, so this angle, the missing angle, must be equal to 90 degrees minus alpha in order to complete the sum of the angles in the right triangle DEF to 180 degrees. This angle must be equal to 90 degrees minus alpha. Okay? But 90 degrees minus alpha equals to theta. So we can substitute this angle that is equal to 90 degrees minus alpha by theta. Okay, we'll do it now. We write down that this angle equals to theta. Okay? In the next step, we will define side DF on this right triangle as x. We will define side EF as y. We will define AE, line segment AE as A. We know that AE equals to EC. It is given as the question that AE equals to EC. So if AE equals to A, then EC must be also equals to A because of the fact that AE equals to EC. So in the next step, we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle EFC. Okay, we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle EFC. Okay? So why the right triangle ABC is similar to the small right triangle, triangle EFC? First of all, we know that those two angles, they are equal to each other, they are both equal to 90 degrees. So angle ABC of triangle ABC is equal to this angle EFC, and both angles, they are right angles, they are equal to 90 degrees. I'll repeat again. Angle ABC equals to angle EFC, and they are both equal to 90 degrees. In addition, here we have already know that 90 degrees minus alpha equals to theta. So here, this angle that is equal to 90 degrees minus alpha, it is actually equals to theta, according to this equation. So here, those two angles, they are equal to each other, they are both equal to theta. So you can write down that angle BAC of triangle ABC is equal to angle FEC of triangle EFC, and both angles are equal to theta. I will repeat again. Angle BAC equals to angle FEC, and they are both equal to theta. Finally, this angle is a common angle. It belongs to both triangles. So we can write down that this angle equals to itself. So this angle, it is actually angle BCA. Angle BCA equals to itself, that is actually also angle FCE, and it is equals to alpha. So it is actually a common angle. I repeat again. Angle BCA equals to angle FCE, that is equal to alpha. So we actually proved that all the angles of triangle ABC can go into all the angles of triangle FEC. Here, those two angles, they are equal to each other, they are both equal to theta. Those two angles, they are equal to each other, they are both equal to 90 degrees. And this angle is a common angle, that is to say, it is equal to itself. Or in other words, this angle belongs to triangle ABC, and it also belongs to triangle EFC. So you can write down that this angle equals to itself. So we actually proved that all the angles of triangle ABC can go into all the angles of triangle FEC. Therefore, triangle ABC is similar to triangle EFC according to angle similarity rule. Okay. Actually, triangle ABC is similar. This is the sign of similar to triangle EFC according to angle similarity rule. And from the fact that triangle ABC is similar to triangle EFC, we will conclude, hence, we conclude that the following relationship exists between their sides. We will conclude that AB over AC is equal to EF over AC. I repeat again, we conclude that AB over AC equals to EF over AC. So AB over AC. AC equals to A plus A, that is 2A. So we substitute AC by 2A. Equals to EF. EF is equal to Y according to our definition. Over AC. AC equals to A according to our definition also. So, in conclusion, we found out that according to equation number 1, AB over 2A equals to Y over A. Here we have A on both sides of equation number 1, so A will get cancelled, and we're left only with AB over 2, that is equals to Y. Here we will multiply this equation number 1 by 2, and we will get that according to equation number 1, AB equals to 2y. Okay, so here you can write down that AB equals to 2y, and in the next step we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, this triangle, triangle EDF. Okay, so we prove that the right big triangle, triangle ABC, is similar to this triangle, triangle EDF. So why those two triangles are similar to each other? First of all, those two angles, they are equal to each other, they are both equal to 90 degrees. So angle ABC of triangle ABC is equal to this angle, angle EFD of triangle EDF, and they are both equal to 90 degrees. I'll repeat again, angle ABC equals to angle EFD, and they are both equal to 90 degrees. In addition, those two angles, they are also equal to each other, they are both equal to alpha. So angle ACB of triangle ABC is equal to this angle, that is actually angle DEF, and they are both equal to alpha. Okay, angle ACB equals to angle DF, and they are both equal to alpha. Finally, those two angles, they are equal to each other, they are both equal to theta. So angle BAC of triangle ABC equals to angle EDF, and they are both equal to theta. I'll repeat again, angle BAC equals to angle EDF, and they are both equal to theta. So all the angles of the right triangle, triangle ABC, can point to all the angles of the right triangle, this triangle EDF. Why? Because those two angles, they are both equal to theta, therefore they are equal to each other. Those two angles, they are both equal to 90 degrees, therefore they are equal to each other. And both those two angles, they are both equal to theta, therefore they are equal to each other. So we proved that the right triangle, triangle ABC, is similar, this is the sign of similar, to the right triangle, triangle EDF, and similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that AB over BC of triangle ABC is equal to DF over EF of triangle EDF. I will repeat again. From the fact that those two triangles are similar to each other, from the fact that triangle ABC is similar to triangle EDF, we derive that AB over BC equals to DF over EF. So according to equation number 2, AB equals to 2y, so we'll substitute AB by 2y. AB over BC. BC equals to 6 units according to what is given us in the question. And according to equation number 2, it is equals to DF. DF equals to X, according to our definition, over EF. EF equals to Y, also according to our definition. So in conclusion, we found out that according to equation number 2, 2y over 6 equals to x over y. Here we will divide both the numerator and the denominator of this side of equation number 2 by 2, and we get that according to equation number 2, 2y over 2 is y, and 6 over 2 is 3, and it is equal to x over y. Here we cross multiply this equation, equation number 2, and we get that according to equation number 2, y squared equals to 3x. Y squared equals to 3x. So according to equation number 2, y squared equals to 3x. But here, if we focus on the right triangle, triangle DEF, in the right triangle, triangle DEF, it is very easy to see that according to the Pythagoras theorem, x squared plus y squared equals to 2 squared. Okay, x squared plus y squared equals to 2 squared, that is 4. So in the right triangle DEF, according to the Pythagoras theorem, by PT is the abbreviation for Pythagoras theorem, x squared plus y squared equals to 4. This is equation number 3. Here we can substitute y squared in equation number 3 by 3x, because 3x equals to y squared according to equation number 2. We'll do it now, and we'll get that according to equation number 3, x squared plus y squared, and y squared equals to 3x according to equation number 2. It is equals to 4. So we found out that x squared plus y squared, this is 3x, equals to 4. Here we will subtract we will subtract 4 from this equation, equation number 3, and we get that according to equation number 3, x squared plus 3x minus 4 equals to 0. So we have here a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c in this general quadratic equation are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X is actually equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. And the variable that we are looking for is x. So we'll put the data inside the equation for x, and we'll find out the value of the values of x. So here we get that x equals to minus b. B is equals to 3, so minus b it is minus 3, plus minus square root of b squared. B equals to 3, so b squared is 3 squared, that is 9. Minus 4 times a is 1, times c is minus 4, so it is minus 4 times minus 4 over 2a. A is 2, so 2 times 1 is 2, so in conclusion we found out that x equals to minus 3 plus minus square root of minus 4 times minus 4 is plus 16, and 16 plus 9 is 25. So inside the root we have only 25. That is what is left, over 2. So here we got that x equals to minus 3 plus minus square root of 25 is 5, and 5 divided by 2. So here we have two solutions that are possible for x. The first solution for x is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So we found out that the first solution is x1 equals to minus 4. That is a negative solution. But here x is the length of side DF of the right triangle DEF. Therefore x as a length must be a positive number. So I write it down. Because of the fact that x is a length, it must be a positive number. So if x can never be equal to minus 4, that is a negative number, so we'll cancel this solution, and we're left only with the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x2 equals to 1. So I will copy the right triangle EDF, and we will find out the cosine theta of this right triangle. Okay? We know that x equals to 1. This is the right triangle in EDF that I copied from the original drawing. This is angle theta. In this right triangle EDF, we know that cosine theta equals to df over dE. df equals to x that is equals to 1, dE equals to 2. It is given us in the question. So in conclusion, we found out that cosine theta equals to 1 over 2, and if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. So the answer to the question is that theta equals to 60 degrees. Here, this angle theta, equals to 60 degrees. Okay, that is the answer to the question. So we finished with the first method. In the next step, I will present to you how to find out the size of this angle theta, according to the second method. In the second method, we define this angle as angle alpha. We know that this angle must be also equals to 90 degrees minus theta. In order to complete the sum of the angles in the right triangle ABC to 180 degrees, we know that this angle equals to 90 degrees. This angle equals to theta, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC to 180 degrees. Okay? So we'll focus on the right triangle ABC. I will copy the right triangle ABC in a new page, and we will analyze the right triangle ABC. We define line segment AE as A, therefore EC must be also equals to A because A equals to EC. So actually, the hypotenuse AC equals to A plus A, that is 2A. So this is the right triangle ABC that I copied from the original drawing. So in the right triangle ABC, we know that cosine alpha equals to BC over AC. That is to say, BC equals to 6 units, this is given as the question, over AC, that is equals to 2A according to our definition. So in conclusion, we found out that in the right triangle ABC, cosine alpha equals to 6 over 2A. So here cosine alpha equals to 6 over 2A. So we'll divide both the numerator and the denominator of this side of equation number 1 by 2. 6 over 2 is 3, and 2A over A is A. Okay? So according to equation number 1, cosine alpha equals to 3 over a. Here we will multiply equation number 1 by a, and then we will divide it by cosine alpha, and we will get that according to equation number 1, a equals to 3 over cosine alpha. Okay? In the next step, we'll focus on the right triangle, triangle EDC. So we'll copy the right triangle, triangle EDC in a new page, and we'll analyze this triangle, triangle EDC. So this is the right triangle, triangle DEC that I copied from the original drawing. This angle equals to 90 degrees, of course. So here, tangents alpha. In the right triangle, triangle EDC. Tangents alpha equals to DE over AC. DE equals to A, DE equals to 2. Here DE equals to 2. And EC equals to A. So in conclusion, I found out that according to equation number 2, tangents alpha equals to 2 over A but according to equation number 1, we've already found out that A equals to 3 over cosine alpha. So we can substitute A in equation number 2 by 3 over cosine alpha, because A equals to 3 over cosine alpha according to equation number 1. So we'll do it now, and we will get that according to equation number 2, tangents alpha equals to 2 over A, but A according to equation number 1 equals to 3 over cosine alpha. So in conclusion, we found out that tangents alpha according to equation number 2 equals to 2 times cosine alpha over 3. Here we'll substitute tangents alpha in equation number 2 by sine alpha over cosine alpha, and we get that according to equation number 2, tangents alpha equals to sine alpha over cosine alpha, and it is equal to 2 times cosine alpha over 3. Here we cross multiply this equation number 2, and we'll get that according to equation number 2, 3 times sine alpha equals to 2 times cosine square alpha. We have the trigonometric identity that states that sinus square alpha plus cosine square alpha equals to 1. Here we'll subtract sine square alpha from this trigonometric identity, and we get that according to this trigonometric identity, cosine square alpha equals to 1 minus sine square alpha. Now you can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We'll do it now, and we'll get that according to equation number 2, three sinus alpha equals to 2 times cosine square alpha, but cosine square alpha according to this trigonometric identity equals to 1 minus sine square alpha. We'll open the brackets on this side of equation number 2, and we get that 3 times sine alpha equals to 2 times 1 is 2, and 2 times minus sine square alpha equals to minus 2 times sine square alpha. We will add 2 sine square alpha to this equation number 2, and we will get that according to equation number 2, 2 sine square alpha plus 3 sine alpha equals to 2. Here we will subtract 2 from this equation number 2, and we will get that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So here we have a quadratic equation, and the coefficients of this quadratic equation here are as follows. The coefficient A equals to 2, the coefficient B equals to 3, and the coefficient C of this quadratic equation equals to minus 2. And the formula for x is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. And the variable that we are looking for in our specific quadratic equation is x equals to sinus alpha. So we'll put the data inside the formula for x, and we'll find out the value or the values of sinus alpha, because x equals to sinus alpha. So we get that sinus alpha equals to minus b, b equals to 3, so minus b is minus 3 plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9, minus 4 times a is 2, times c is minus 2, over 2a. A is 2, so 2 times 2 is 4. So here we get that sinus alpha equals to minus 3 plus minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16, and 16 plus 9 is 25. So inside the root we have only left with 25 over 4. So here sinus alpha equals to minus 3 plus minus square root of 25 is 5 over 2. So here we will have two solutions that are possible for sinus alpha. The first solution for sinus alpha is the sinus alpha equals to minus 3 minus 5 over 4, of course. Minus 3 minus 5 is minus 8. And minus 8 over 4 is minus 2. So we found out that the first solution for sinus alpha is the sinus alpha equals to minus 2. But because of the fact that the function sinus can accept values that are ranging from minus 1 to plus 1, and minus 2 exceeds this range of values that sinus alpha can accept, so this solution is an incorrect solution. That is to say, sinus alpha can never be equal to minus 2. Therefore, this solution is a correct solution, and we're left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2, and if sinus alpha equals to 1 over 2, it means that alpha itself will be equal to 30 degrees. So we found out that alpha equals to 30 degrees, and we have already found out that alpha equals to 90 degrees minus theta. Here alpha equals to 90 degrees minus theta. We substitute alpha by 30 degrees because alpha equals to 30 degrees, and we will get that 30 degrees equals to 90 degrees minus theta. Here we will add theta to this equation, and we will subtract 30 degrees, and we will get that theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees is 60 degrees, so we found out that the missing angle, the angle that we are looking for, angle theta, equals to 60 degrees. And that is the answer to the question. That angle theta equals to 60 degrees. This angle theta equals to 60 degrees. This is the angle that we are looking for. Okay? So we finished with the second method. In the next step, I will summarize the lecture. We'll start with the first question. in the first question, we have a semicircle that is inscribed by a quarter circle. We know that the radius of the quarter circle is equal to 3 units, and we want to find out the area of the semicircle that is inscribed by this quarter circle. So we define the center of this quarter circle, we define the center of this semicircle as point O, and then I present it to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle, and we know that tangent AB is tangent to this circle at point M, this is the point of tendency, point M is the point of tendency of tangent AB with this circle, and we have the radius OM that is drawn to the point of tendency, that is to say the radius OM is drawn to the point M, that is the point of tendency of tangent AB with this circle. Then, whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO. That is to say, this angle equals to 90 degrees, and this angle will be equal to 90 degrees, also according to rule number 1. So we can implement rule number 1 in our drawing. Here from point O, we drew the radius OB that is drawn to the point of tendency. That is to say, the radius OB of this semicircle, it is drawn to point B, that is the point of tendency of tangent AC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent AC will be perpendicular to the radius BO. So AC is perpendicular to BO, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Okay, likewise, we drew the radius OD. So we join points O and D together. So OD is the radius that is drawn to the point of tendency. That is to say, the radius OD of the semicircle, it is drawn to point D, that is the point of tendency of tangent CH with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent CH will be perpendicular to the radius DO. So CH is perpendicular to DO, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So we have here two right angles inside quadrilateral BO DC, and because of the fact that ACH is a quarter circle, point C must be the center of the quarter circle, and angle ACH must be equal to 90 degrees. In any quarter circle, here point C must be the center of the circle, the center of the quarter circle, and ACH must be equal to 90 degrees. So actually angle ACH equals to 90 degrees. So in quadrilateral BC, in quadrilateral BOCD, we have three right angles. 1, 2, 3. And the sum of three right angles is 90 times 3, that is 270 degrees. So the sum of the three right angles, that is 270 degrees, plus the size of the fourth angle, that is actually angle BOD. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here, we subtracted 270 degrees from this equation, and found out that the missing angle BOD equals to 360 degrees minus 270 degrees, it is 90 degrees. So here the missing angle, this angle is the right angle, it is equal to 90 degrees. Therefore, in quadrilateral BOCD, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. Therefore, we will relate to quadrilateral BOCD as a rectangle. Okay, here quadrilateral BOCD is a rectangle because it has 4 right angles. And we have also rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of rectangle BOCD are equal to each other. What does it mean? It means that BO equals to CD. Okay, according to rule number 2, that the opposite sides of a rectangle are equal to each other, BO must be equal to CD. But we have already found out that BO is equals to R. It is the radius of the semicircle. Here we can write down that BO equals to R. And from this equation, R equals to BO equals to CD, we will derive that CD is also equals to R. That is the radius of the semicircle. Here, CD also equals to R. That is the radius of the semicircle. Likewise, according to rule number 2, OD must be equal to BC. Okay? According to rule number 2, OD also must be equal to CD. Here, OD must be also equal to BC. Okay, here OD must be equal to BC according to rule number 2, that the opposite sides of a rectangle are equal to each other. But we have already found out that OD equals to R. Here OD equals to R, according to what we have already found out. And from this equation R equals to OD equals to BC, we will derive that BC is also equals to R. Here, BC is also equals to R, therefore we actually found out that all the sides of quadrilateral BOCD are equal to each other, they are all equal to R. So quadrilateral BOCD has 4 equal sides and also 4 right angles. Therefore, quadrilateral BOCD is not a rectangle but a square. So here, quadrilateral BOCD is a square. We join together points C and O by a straight line. So diagonal CO is the diagonal of square BOCD. And we found out the length of diagonal CO of square BOCD by implementing the Pythagoras theorem on the right great triangle, triangle COD. According to the Pythagoras theorem on the right triangle COD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say CO square equals to CD square plus DO square. In the right triangle, triangle OCD, CO square equals to CD square plus OD square. So CO square equals to CD squared, CD equals to R, so CD square equals to R square. Here, CD square equals to R square plus OD square. OD equals to R, so OD square will be equal to R square also. So OD square also equals to R square. So in conclusion, we found out that OC square equals to R square plus R square. R square plus R square is 2R square, so in conclusion we found out that OC square equals to 2R square. We took out of this equation and we found out that OC equals to square root of 2R. So the diagonal OC of this square equals to square root of 2R units. Then we extended diagonal CO by a straight line until it touches the quarter circle at point S. So here we created line segment OS and we found out the length of line segment OS. It is very easy to see from the drawing that the length of line segment OS equals to CS minus CO. Again, CS minus CO equals to the length of line segment SO. I'll repeat again. SO, the length of line segment SO equals to CS or SC minus OC. what is the length of CS? C is the center of the quarter circle, and S is the point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, CS is the radius of the quarter circle that is equal to 3 units. So CS equals to 3 units, and we have already found out that CO equals to square root of 2 times R, that is the diagonal of the square. So in conclusion, we found out that SO equals to 3 minus square root of 2R. So you can write here that the length of this small line segment, SO equals to 3 minus square root of 2R. Then we completed the quarter circle to a circle. In the next step, we extended the diagonal CO by a straight line until it touches the circle at this point, point M. So what is the length of MC? C is the center of the circle. M is the point of the circle itself. And this is exactly the definition of a radius. That is to say, CM is equal to the radius of the circle. That is also the radius of the quarter circle. And we know that the radius of this quarter circle equals to 3 units. So MC equals to 3 units. Okay, then I presented to you a new rule, that is rule number 3. According to rule number 3, if chord AB intersects with chord CD at point O, then the following formula is true, that AO times OB equals to CO times OD. I'll repeat again on rule number 3. If we have chord AB that intersects with chord CD inside this circle, the intersection point is at point O. The intersection point between chord AB and chord CD is at point O. Then the following formula is true, or the following relationship exists between the parts of the two chords. AO times OB equals to CO times OD. Okay? We actually implemented rule number 3 in our drawing. In our drawing, we have chord SM that is the sex with chord GF at point O. Point O is the intersection point of chord SM with chord GF. Therefore, according to rule number 3, I'll repeat again here that in our drawing we have chord SM that intersects chord SM that intersects with chord GF at point O. Point O is the intersection point of chord SM with chord GF. Therefore, according to rule number 3, we get that MO times OS equals to GO times OF. Okay? I'll repeat again. According to rule number 3, MO times OS equals to GO times OF. Okay? MO, what is the size of MO? It is very easy to see from the drawing that MO equals to MC plus CO. Okay, MO equals to MC plus CO. We have already found out that SO equals to 3 minus square root of 2R. GO is the radius of the semicircle. OF is also the radius of the semicircle. So GO times OF equals to R times R. R times R is R squared. MC equals to 3 units. CO equals to square root of 2 times R. So MC plus CO equals to 3 plus square root of 2R. We have already found out that SOS equals to 3 minus square root of 2R, and that is equal to R squared. Here, this expression is very similar to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. So this expression equals to A squared minus B squared, when A equals to 3 and B equals to square root of 2R. Therefore, A squared is 3 squared, that is 9, minus B squared. B squared is square root of 2R squared, that is actually square root of 2, that is 2, times R squared. So in conclusion, I found out that this expression equals to 9 minus 2R squared, that is equals to R squared. We added 2r squared to this equation and found out that 9 equals to r squared plus 2r squared is 3r squared. We divided this equation by 3 and we found out that 3r squared over 3 equals to r squared and 9 over 3 is 3. So in conclusion, we found out that r squared equals to 3. And the area of the semicircle equals to the area of the circle, that is pi r squared over 2. So the area of our semicircle equals to pi r squared over 2. R squared equals to 3, so we can substitute r squared in this equation by 3. We need it, and we got that pi times r squared, that is 3 over 2, equals to the area of the semicircle. So in conclusion, we found out that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first method. The next step, I will present to you how we found out the area of the semicircle according to the second method. Okay, in the second method, we actually use the things that we already found out in the first method. Here we know that BOCD is a square, and we already found out that the diagonal of this square CO equals to square root of 2 times R. We already found out that here OF equals to the radius of the semicircle, that is R, and GO is also the radius of the semicircle, that is R. And then here we actually connected point C and G together by a straight line. CG is the radius of the quarter circle. Why? Because it starts from point C, that is the center of the quarter circle, and ends at point G, that is the point of the quarter circle itself. Therefore, CG is the radius of the quarter circle, that is to say it is equal to 3 units. Likewise, here we have CF. We join point C and F together by a straight line, and line segment CF, it is also the radius of the semicircle, the radius of the quarter circle, for the same reason. Why? Because it starts from the center of the quarter circle, that is to say from point C, and ends at point F, that is the point of the quarter circle itself. Therefore, CF is the radius of the quarter circle, that is equal to 3 units. So here we created the isosceles triangle GCF. Why triangle GCF is an isosceles triangle? Because of the fact that sine CG equals to sine CF, they are both equal to 3 units. So I copied the right triangle CGF in a new page. This is the right the isosceles triangle. This is the isosceles triangle CFG. CF equals to 3 units, CG is also equals to 3 units. CO is the median to the base FG. FG is the base of the isosceles triangle CFG, and CO is the median to the base. Why CO is the median to the base? Because of the fact that line segment CO divides the base GF into 2 equal parts. That is to say, OG equals to OF equals to R. Okay? Again, the base of the isosceles triangle CFG is FG, and the median to the base is CO. And here we have rule number 4 that is related to the median to the base of an isosceles triangle. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So the median CO to the base FG is not only divides the base into 2 equal parts, but it is also perpendicular to the base. So CO is perpendicular to FG, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. And repeat again on rule number 4, the median to the base, that is to say CO is the median to the base FG, is perpendicular to the base FG. So the median CO is perpendicular to the base FG. So CO is perpendicular to FG, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. So the median CO to the base GF divides the associated triangle CFG into two right triangles that are identical to each other. So we choose to take the right triangle CFO, and we implemented the Pythagoras theorem on this right triangle CFO. In this right triangle CFO, according to the Pythagoras theorem, first of all, according to rule number 4, the median CO to the base GF is perpendicular to the base GF. So CO is perpendicular to GF. That is to say this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 4. So I copied the right triangle COF in a new page, and we implemented the Pythagoras theorem on the right triangle COF. We know that CO is the diagonal of the square that is equal to square root of 2 times r. It is also the median to the base. FO is the radius of the semicircle that is equal to r, and we already found out that CF is the radius of the quarter circle, that is to say it is equal to 3 units. So we implemented the Pythagoras theorem on this right triangle CFO according to the Pythagoras theorem. PT is the abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is CF, the square of the hypotenuse is CF square, and it is equal to the sum of the squares of the perpendiculars, that is to say it is equal to CO square plus FO square. CF is 3, so CF square is 3 squared, that is 9, and it is equal to CO square. CO is square root of 2r, so CO square is square root of 2r squared, that is 2r square, plus FO square. FO is r, so FO square is r square. So in conclusion, we found out that 9 equals to 2r square plus r square. 2r square plus r square is 3r square. So we got that 3r square equals to 9. We divided this equation by 3 and we got that r square equals to 3. So we know that the area of the semicircle equals to pi r square over 2, because it is half the area of the square, half the area of the circle, and half the area of the circle is pi r square over 2, and r square equals to 3, so we can substitute r square by 3. We did it, and we got that pi r square equals to pi times 3 over 2. Okay, so in conclusion, we found out that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first question. In the next step, I will present to you how we solved the second question in two different methods. Okay? In the second question, we have in the drawing the right triangle ABC. You know that angle ABC equals to 90 degrees. Side BC of the right triangle ABC equals to 6 units. And we know also that AE equals to EC. And we also know that line segment DE equals to 2 units. And DE is perpendicular to AC, the hypotenuse AC. That is to say this angle equals to 90 degrees and this angle equals also to 90 degrees. Okay, and we want to find out the size of this angle theta. In order to find out the size of angle theta, we made a construction. From point E, we drew perpendicular on BC, so this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. And we define the touching point of the perpendicular from point E on BC as F. So here, in the next step, we define this angle as angle alpha. From one side, this angle equals to alpha according to our definition. But from the other side, this angle must be also equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC to 180 degrees. This angle also must be equal to 90 degrees minus theta. So in conclusion, we can derive from it that alpha equals to 90 degrees minus theta. Okay, alpha equals to 90 degrees minus theta. We added theta to this equation and we subtracted alpha, and we got that theta equals to 90 degrees minus alpha. Then, so if this angle equals to alpha, this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in the right angle FEC to 180 degrees. This angle must be equal to 90 degrees minus alpha. But we know that 90 degrees minus alpha equals to theta. So we can write here that 90 degrees minus theta equals to theta. Here again, 90 degrees minus alpha equals to theta. Therefore, we can write here that 90 degrees minus alpha equals to theta according to this equation. And then we found out the size of this angle. Angle DFE will be equal to angle DEC minus angle FEC. Again, the big angle DEC minus this angle, that is angle FEC, will be equal exactly to this angle DEF. So here again, angle DEF equals to the big angle DEC minus angle FEC. It is given us the equation that this angle, the big angle, is the right angle. It is equal to 90 degrees. We have already found out that this angle FEC equals to 90 degrees minus alpha. So in conclusion, angle DEF equals to 90 degrees minus 90 degrees minus alpha. We open the brackets here and we found out that this angle DEF equals to 90 degrees minus 90 degrees, that is 0, minus and minus is plus. So angle DEF equals to alpha. So here, this angle, the missing angle DEF equals to alpha. So in the right triangle DEF, in this angle equals to alpha, this angle equals to 90 degrees, this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right triangle DEF to 180 degrees. So this angle equals to 90 degrees minus alpha. But because of the fact that 90 degrees minus alpha equals to theta, we can substitute this angle that is equal to 90 degrees minus alpha by theta. We did it, so therefore angle EDF equals to theta. Okay? Then we define DF as x, we define EF as y, we define AE as A, and EF must be also equal to A because AE equals to AC. So if AE equals to A, then EC must be also equal to A. Then we prove that the right triangle ABC is similar to the right triangle EFC, this right triangle. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to theta. Those two angles are equal to each other, they are both equal to 90 degrees. And finally, this angle is a common angle. It belongs to both triangles, so we can write down that this angle equals to itself. So we actually proved that all the angles of triangle ABC can go into all the angles of triangle EFC. Therefore, we proved that the right triangle ABC is similar to the right triangle EFC according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over AC equals to EF over EC. Again, according to question number 1, AB over AC equals to EF over EC. So AB over AC equals to A plus A, that is 2A, so we can substitute AC by 2A. EF equals to Y according to our definition, and EC equals to A according to our definition. So in conclusion, we found out that according to question number 1, AB over 2A equals to Y over A. Here we have A on both sides of the question number 1, so A will get cancelled, and we left only with AB over 2, that is equals to Y. Here we multiply this equation number 1 by 2, and we got that AB equals to 2Y. So here we can write down that AB equals to 2Y. Then we proved that the right small triangle DEF is similar to the right big triangle ABC. Write those two right triangles are similar to each other? First of all, those two angles that are equal to each other, they are both equal to alpha. In addition, those two angles that are also equal to each other, they are both equal to 90 degrees. And finally, those two angles that are equal to each other, they are both equal to theta. So we prove that all the angles in the right big triangle ABC can go into all the angles in the small right triangle in the F. Therefore, triangle ABC is similar to triangle ADF according to angle, similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that AB over BC equals to DF over EF. Again, AB over BC equals to DF over EF. Okay? AB equals to 2y. So we substitute AB by 2y. BC equals to 6 units, it is given as the question, so we substituted BC by 6. DF equals to x according to our definition, and EF equals to y according to our definition. So in conclusion, we found out that according to question number 2, 2y over 6 equals to x over y. Here we divided both the numerator and the denominator of this side of equation number 2 by 2. 2y over 2 is y, and 6 over 2 is 3. So in conclusion, we found out that according to equation number 2, y over 3 equals to x over y. We cross multiply this equation number 2, and we found out that y squared equals to 3x. So according to equation number 2, y squared equals to 3x. But if we focus on the right triangle DEF, if we implement the Pythagoras theorem on this right triangle DEF, we will get that x squared plus y squared equals to 2 squared. So in the right triangle DEF, according to the Pythagoras theorem, we will get that x squared plus y squared equals to 2 squared, that is 4. Now we can substitute y squared in this equation number 3 by 3x. Why? Because according to equation number 2, y squared equals to 3x. So we did it, and we got that according to equation number 4, according to equation number 3, x squared plus y squared, that is 3x, according to equation number 2, equals to 4. Here we subtracted 4 from this equation number 3, and we got that according to equation number 3, x squared plus 3x minus 4 equals to 0. So here we have a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. A, b, and c in this general formula are the coefficients of the quadratic equation, and x is the variable that we are looking for. And if we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we put the data inside this equation, and we found out the value of the values of x. Here x equals to minus b equals to 3, so minus b is minus 3, plus minus square root of b squared, b equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, times c is minus 4. So here inside the root we have minus 4 times minus 4 is 16, and 16 plus 9 is 25. So in conclusion, we found out that x equals to minus 3 plus minus square root of 25 over 2. Square root of 25 is 5, so in conclusion, we found out that x equals to minus 3 plus minus 5 over 2. So here we have two solutions that are possible for x. The first solution, x1 is x1 equals to minus 3 minus 5, that is minus 8. Minus 8 over 2 is minus 4, so x1 equals to minus 4. But because of the fact that x is length, it cannot be a negative number. So we cancel this solution, and we left only the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x2 equals to 1. Then I copied the right triangle DEF in this new page, and we found out that cosine theta of this right triangle ADF. In this right triangle ADF, cosine theta equals to df and cosine theta equals to EF, cosine theta equals to DF over EF. Cosine theta equals to DF over here, cosine theta equals to DF over FE. Here cosine theta equals to, it is actually cosine theta equals to DF over DE. Again, cosine theta here equals to DF over DE. DF equals to 1, DE equals to 2, so cosine theta equals to 1 over 2. And if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. So we found out that theta equals to 60 degrees. Then I presented to you the second method to find out the value of cosine theta. In the second method, we define this angle as alpha. So, but this angle is also equals to 90 degrees minus theta, therefore alpha equals to 90 degrees minus theta. Then we focused on the right triangle ABC. In the right triangle ABC, we know that cosine alpha equals to BC over AC. BC equals to 6 and AC equals to 2A. So in conclusion, we found out that cosine alpha equals to 6 over 2A. We divided both the numerator and the denominator on this side of equation number 1 by 2, and we got that 6 over 2 is 3, and 2A over 2 is A. So in conclusion, we found out that cosine alpha equals to 3 over A. Here, we multiply this equation by A, and then we divide it by cosine alpha, and we got that A equals to 3 over cosine alpha. Then we focused on the right triangle DEC. So in the right triangle DEC, this right triangle, we know that tangent alpha equals to DE over EC. DE equals to 2, EC equals to A. So in conclusion, we found out that tangent alpha equals to 2 over A. But according to equation number 1, we have already found out that A equals to 3 over cosine alpha. So we can substitute A in this equation number 2, by 3 over cosine alpha. We did it and we got that tangent alpha equals to 2 over A, and A equals to 3 over cosine alpha. So in conclusion, we found out that tangent alpha equals to 2 times cosine alpha over 3. Tangent alpha equals to sinus alpha over cosine alpha, so we substituted tangent alpha by sinus alpha over cosine alpha, and we got that sinus alpha over cosine alpha equals to 2 cosine alpha over 3. We cross multiply this equation number 2, and we found out that 3 times sine alpha equals to 2 times cosine square alpha. Then we have the trigonometric identity that sine square alpha plus cosine square alpha equals to 1. We subtracted sine square alpha from this trigonometric identity, and we got that cosine square alpha equals to 1 minus sine square alpha. So we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We did it, and we got that 3 sine alpha equals to 2 times cosine square alpha. But cosine square alpha, according to this trigonometric identity, equals to 1 minus sine square alpha. Here we open the brackets, and we got that 3 sine alpha equals to 2 times 1 is 2, and 2 times minus sine alpha equals to minus 2 times sine square alpha. We added 2 sine square alpha to this equation, and we got that 2 sine square alpha plus 3 sine alpha equals to 2. We subtracted 2 from this equation, and we got that 2 sine square alpha plus 3 sine square alpha minus 2 equals to 0. So here we have a quadratic equation. The coefficients of this quadratic equation are as follows. The coefficient A equals to 2, the coefficient B equals to 3, and the coefficient C equals to minus 2. And the solution to this quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. And the variable that we are looking for in this specific quadratic equation is sinus alpha. So x equals to sinus alpha. We put the data inside the equation for x and found out that sinus alpha equals to minus b equals to 3. So minus b is minus 3 plus minus square root of b squared. B equals to 3. So b squared is 3 squared, that is 9. Minus 4 times a is 2 and c is minus 2. So it is minus 4 times 2 times minus 2 over 2a. A is 2, so 2 times 2 is 4. So in conclusion, we found out that sinus alpha equals to minus 3 plus minus. Here minus 4 times 2 is minus 8, and minus 8 times minus 2 is 16. 16 plus 9 is 25. So in conclusion, we found out that sinus alpha equals to minus 3 plus minus square root of 25 over 2. Square root of 25 over 4. Square root of 25 is 5, so here we found out that sinus alpha equals to minus 3 plus minus 5 over 4. So here we have two solutions that are possible for sinus alpha. The first solution for sinus alpha is sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8. Minus 8 over 4 is minus 2. So in conclusion, we found out that sinus alpha equals to minus 2, but because of the fact that the range of values that sinus alpha can accept, they are ranging from minus 1 to plus 1, and minus 2 exceeds this range of values that sinus alpha can accept. So this solution is a correct solution. Why? Because sinus alpha can never be equal to minus 2. So we left only in the second solution that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2. And we have the equation that alpha equals to 90 degrees minus theta. So here we can write down that alpha equals to 90 degrees minus theta. And we can substitute alpha by 30 degrees because alpha equals to 30 degrees. And we got that 30 degrees equals to 90 degrees minus theta. Here we added theta to this equation and we subtracted 30 degrees and we found out that theta equals to 90 degrees minus 30 degrees. This is 60 degrees. So in conclusion, we found out that angle theta equals to 60 degrees. Okay? Thank you very much.